Today we're going to look at a new unit for angles called radians. So far in your lives you've only ever met degrees. 360 degrees in a full circle, 180 degrees on a straight line, 90 degrees in a right angle. But that's not really got much mathematical significance other than thousands of years ago the Babylonians thought there's about 360 days in a year, so let's have 360 degrees in a circle. And it's got lots of factors, so it divides up quite nicely. It's worked quite well. But more recently we've moved to a metric system for everything. It makes sense that because our number system is based around the number 10, that we use a base 10 for our units of measure as well. So how about having 100 degrees in a right angle and 400 degrees in a circle? Except in this new system they're not called degrees, they're called gradients. So still not the radians that we want to be looking at today. That works better because it works with our base 10 number system, but it's still not got a mathematical reason behind it. And the radians that we're going to look at today have a mathematical basis. So in a circle, if you have a radius of r, there will be a sector where the length of the arc is the same as the radius. And the angle in that sector we call a radian. We use this superscript C to stand for radians, a bit close to the degree symbol, I know, but that's what we use. So we have 1 radian in the centre of a sector whose arc length is the same as its radius. And we know that the radius fits around a circle 2 pi times. We know that the circumference of a circle is pi times the diameter, so 2 pi times the radius. So if I were to draw in more of these sectors, which have an arc length of r, I would fit pi, 3 and a bit of them, in half a circle, and 2 pi, 6 and a bit of them within a whole circle. So at the centre of my circle I have 6 and a bit radians, it's 2 pi radians. So although it's not a nice number, in fact it's an irrational number, within a whole circle, 360 degrees, we have 2 pi radians. And we often leave our answers when we're working in radians in terms of pi, rather than trying to approximate that irrational number. We can put that C to stand for the radian symbol, but we quite often don't bother if we're in terms of pi, because the only angles unit that we leave in terms of pi is radians anyway. So 360 degrees would be 2 pi, 180 degrees is pi. That is our main conversion fact that we're going to use to help us to convert between degrees and radians. We're going to look at converting between degrees and radians today, but we're going to try really hard not to get into the habit of doing that, but to work in one unit or the other. So to solve problems thinking in degrees, or to solve problems thinking in radians. So let's have a look at the notes for today. We've already talked about this bit at the top. We use radians a lot because of this natural relationship between circles and radians, and that means that they become really helpful for us when working with trigonometry and calculus, which we haven't yet met, but we can once we've learnt about radians. So a lot of the things that you have been doing over the last however many years you've been in school, 12 years, will now need to be relearnt working with radians rather than degrees. So let's start by converting, in example 1, some degrees into radians. Now we said 180 degrees is pi radians, and we've got some nicely related angles here. So if 180 degrees is pi radians, 90 degrees is half of that. So we can write that as a half pi or as pi over 2. 45 degrees is a quarter of 180 degrees. So it's a quarter pi or pi over 4. 30 degrees is 180 degrees divided by 6. So it's a sixth of pi or pi over 6. 60 degrees is double that. So 2 pi over 6 or pi over 3. 120 degrees is double 60 degrees, so 2 pi over 3. 135 degrees is 90 degrees plus 45 degrees, so 3/4 pi. 150 degrees is 5 lots of 30 degrees, so 5 pi over 6. 240 degrees is 2 lots of 120 degrees, so 4 pi over 3. 270 degrees is 180 degrees plus 90 degrees, so 3 pi over 2. And 315 degrees is 270 degrees plus 45 degrees, so 7 pi over 4. So once you know that pi is 180 degrees, these common angles become quite straightforward to work out. If we've got something more complicated like 39.24 degrees, we may need to think a little bit harder. But I know pi radians is 180 degrees, so if I divide that fact by pi, 1 radian is 180 divided by pi. Or if I divide that fact by 180, then 1 degree is pi over 180 radians. So 39.24 degrees is pi over 180 times 39.24. So 1 degree is pi over 180, so 39.24 degrees is pi over 180 times 39.24. Or if we look at how it tells us to do it on the sheet, to convert degrees to radians, divide by 180 times by pi, which is what we're doing here. And then that would just be a case of typing it into your calculator. So we want to do pi over 180 times 39.24. We get 0.68 radians to 2 decimal places. And then if we do the same thing with the other angle, it's a negative angle, so that means we're working anti-clockwise. So minus 280.49 times pi over 180 gives us minus 4.90 radians. And we can put that little C symbol to tell us we've now got radians. So to convert radians into degrees, well, 11 pi over 12, we know pi in degrees is 180, so we can just change the pi into 180. So we've got 11 twelfths of 180 degrees, so 165 degrees. And then the 1.637 radians, we can use this fact here. 1 radian is 180 divided by pi, so we're going to have 1.637 lots of that. Or using the method that it's written here, to convert radians to degrees, we're dividing by pi and we're multiplying by 180. So 1.637 times 180 and divide by pi. So we get 93.79 degrees. Okay, so that's converting between the units. Let's have a look at using this alongside some Year 12 knowledge in solving equations. So in this question, we want theta between 0 and 2 pi. We're used to doing it between 0 and 360 degrees. So the method's going to be very similar. We just need to be thinking in terms of radians instead of in terms of degrees. So 2 sine theta plus 1 is 0. That means sine theta is minus a half. So I'm going to want to work out theta. That is one of the angles that we one of the exact values that we should know but perhaps don't because we've got lazy and are used to using a calculator now. But you need to make sure if you want to be working in radians that you tell your calculator that. Because if your calculator is in degrees mode, which mine is, there's a little D at the top of the screen, then when I tell it to do inverse sine of a half, it will tell me the answer is 30 degrees. But if I put it into radians mode, by going into setup, so shift setup, option 2 for angle unit and option 2 for radians, now if I do sine inverse of a half, it will tell me that my answer is pi over 6. Now I actually want sine inverse of minus a half, which is minus pi over 6. So my calculator can give me my answer in radians. Don't forget that we need to consider all of the possible answers within the range. So we want to go from 0 to 2 pi. Now we know the sine graph looks like this for the first 360 degrees, and 360 degrees is 2 pi radians. We also know there is a feature of the sine graph every 90 degrees, and in radians that would be every pi over 2 radians. So we pass through the origin, then pi over 2 units later we have a maximum, pi over 2 units later, so at pi we have another x-intercept, pi over 2 units later we have the minimum, and then pi over 2 units later we have the other x-intercept. So sine theta is minus a half, has a root at minus pi over 6. That's outside the range, so we're not going to use it as an answer, but we can use it to help us to find answers within the range. So if I extend my graph backwards, I can see here that at minus pi over 6, I have that minus a half value. And if I read across, I'm going to have 2 values in the range. Now I need to use the symmetry of the graph here to help me to find those values. So I know that if this distance here from the origin to my solution is pi over 6, then from my x-intercept to my solution will also be pi over 6, and from my other x-intercept to this value will also be pi over 6. So my values of theta within the range are pi plus pi over 6 and 2 pi minus pi over 6, which gives me 7 pi over 6 and 11 pi over 6. So those are my 2 values within the range. Right, for the next question, sine 3 theta over root 3 is cos 3 theta. We know if we've got an equation with sine theta and cos theta, we can rearrange it to make tan theta. So if I rearrange this, sine 3 theta over cos 3 theta is root 3. So that tells me that tan 3 theta is root 3. So I can use my calculator to get my principal value. So inverse tan of root 3 is pi over 3. So that is my value for 3 theta this time. Now the range is from 0 to 2 pi, but that is for theta. We're now working with 3 theta. So we need to multiply our range by 3, and we need to be considering values between 0 and 6 pi. Now we know the tan graph. It's the funky one that looks like this with loads of asymptotes. And we know it repeats itself every 180 degrees. So that's every pi radians. So if we have a value at pi over 3, we will also have a value 180 degrees later, pi radians later, and another one, another pi radians after that. So once we've got one value, we can add or subtract pi to get our remaining values. So if I subtract pi, I'm going to be outside the range. So let's just keep adding pi. So that's going to be 4 pi over 3, or 7 pi over 3, or 10 pi over 3, or 13 pi over 3, or 16 pi over 3. If I go any further, I'm going to get to 19 pi over 3, which is bigger than 6 pi. So I'm going to stop there with those 6 values. That's my values for 3 theta. So for theta, I'm going to divide each of those by 3. So I'm going to have pi over 9, or 4 pi over 9, or 7 pi over 9, or 10 pi over 9, or 13 pi over 9, and finally 16 pi over 9. Okay, on to question C. Cos squared of theta minus pi over 9 is 1. So let's square root this. So that would mean that cos of theta minus pi over 9 is positive or negative 1. So let's consider those 2 possible equations. Cos of theta minus pi over 9 is 1, and cos of theta minus pi over 9 is minus 1. Now we need to consider these values for theta between 0 and 2 pi. So that means if I take pi over 9 away from those values in the range, I want theta minus pi over 9 to be between minus pi over 9 and 2 pi minus pi over 9, or 17 pi over 9. So my cos graph, I know, looks like this, and I know something interesting happens every pi over 2 radians. So this is 0, this is pi over 2, this is pi, this is 3 pi over 2, and this is 2 pi. Now I need to just consider the range needs to be from minus pi over 9, so it's going to go a little bit further beyond the 0 to the left hand side. So let's have a look at values between minus pi over 9 and 17 pi over 9, where cos is 1, and that is just at 0 degrees. 2 pi will be outside the range, so the only one is 0. So theta minus pi over 9 could be 0. And the only place where it's minus 1 is when the angle is pi. So theta minus pi over 9 equals pi. So I've found my 2 values for theta minus pi over 9. So if I add pi over 9 to them, I get my values for theta. And then finally, question 5. This is a quadratic trigonometric equation. So we know how to solve those. We need to start by making sure that they only involve one trigonometric function. So let's replace the sine squared x with 1 minus cos squared x. So now everything is in terms of cos x. And expanding it out is going to give me 6 cos squared x plus cos x minus 1 equals 0. So this is a quadratic equation. We can consider factorising it, or we can use our calculator to treat it as a quadratic equation. So using the equations option on our calculator, it's a polynomial degree 2 with 6 of the squareds, 1 of the plane variable, and minus 1 as our constant. And we get the solutions 1/3. So that's our solution for cos x, because our quadratic was in cos x. And we get minus 1/2. So we want x to be between 0 and 2 pi. So let's use our calculator to use inverse cos to get our first value. Inverse cos of 1/3 gives us 1.23. It says give our answers in terms of pi where appropriate. It's not appropriate, so let's just choose to do this to 3 significant figures. And we need to consider any other roots between 0 and 2 pi. So if we've got 1.23 radians, we will also have a value 1.23 radians back from 360. So if our distance to the root is 1.23 from 0, it will be 1.23 back from that 360 degrees, or 2 pi in this case. So we need to be doing 2 pi minus that 1.23. So those are our solutions to cos x is a third. So let's try cos x is minus a half. So inverse cos of minus a half gives us 2/3 pi. Or if we've got 2/3 pi, we're now looking at a negative value, so we're looking at this distance here being 2/3 pi. So it will be 2/3 pi back from 2 pi as well, or 4/3 pi. 2 pi minus 2/3 would be 4/3 pi. So those are our 4 possible roots to that quadratic equation. For part B, we have exactly the same quadratic equation, except it now is in terms of 2x instead of being in terms of x. So all of our working is going to be exactly the same, except we're going to come down to having 2x is 1.23 radians, or 5.05 radians, or 2/3 pi, or 4/3 pi. We don't need to look for any other values because our initial range was for x between 0 and 2 pi, and our new range is for x between 0 and pi, which means our 2x, which are the angles that we found, need to be between 0 and 2 pi, which we've already got. So our 2x we've already worked out between 0 and 2 pi, so to work out x we just need to half each of those. So half of the 1.23 gives us 0.615 radians. Half of the 5.05 gives us 2.53 radians. Half of 2/3 pi gives me 1/3 pi, and half of 4/3 pi gives me 2/3 pi. So the only new content for today is on understanding what a radian is and being able to convert between them. This is not new content, it's just combining that radians information with what you can already do. So for practice for this, using the worksheet, I'd like you to answer the questions that I've highlighted. So for questions 1, just parts 5, 6, 7 and 8, unless you're feeling really enthusiastic. For question 2, parts 9, 10, 11 and 12. For question 3, parts D, E and F, and then all of questions 4, 5 and 6, please. I'll send out the model solutions so that you can check your answers as you go.